In the previous chapter, we discussed how Maxwell's theory of electromagnetic waves showed the waves move in a vacuum at the speed of light. It was natural then to conclude that light itself was an electromagnetic wave. In the next few chapters, we will introduce various properties of light. We will see that light can reflect off of surfaces, like a mirror for example, and light can pass through certain materials, like a glass prism. In each case, the behavior of the light can be understood in terms of physical principles. We know from experience that mirrors and lenses can form images of objects that we can see with our eyes, if the light falls in the visible part of the electromagnetic spectrum. The branch of physics that involves studying the properties of light is called optics. In the next two chapters, we will focus on geometrical optics, where the propagation of light is described in terms of rays. This approach will allow us to understand images formed by the reflection of light off of surfaces, like a mirror, and the refraction or bending of light as it passes through certain materials, like lenses. From there, we will turn to physical optics, where we consider the propagation of light in terms of its wave properties. Here we will see that when light passes through openings with dimensions that are comparable to the wavelength of the light itself, we observe the phenomena known as interference and diffraction, which are not explained by geometrical optics. Before we begin our study of optics, it is necessary to consider the concept of rays. We are all familiar with mirrors. They are located in our homes, especially in bathrooms, and we see images of ourselves in the mirror because some of the light in the mirror bouncing off of us reflects off the mirror and back into our eyes. In order to describe the reflection process, it is necessary to introduce the concepts of wave fronts and rays of light. To begin, let's first consider sound waves, which we studied previously in Chapter 16. Both sound waves and electromagnetic waves can be described in terms of wave fronts and rays. Imagine a point source of sound vibrating with simple harmonic motion. Sound waves are produced that propagate out away from the source in all directions. To represent these waves, we draw surfaces through all the points of each wave that are in the same phase, for example, all the condensation points. These surfaces of constant phase are called wavefronts and are represented by concentric spherical shells. In the figure, we show them as hemispheres for clarity. The distance between each wavefront corresponds to the wavelength of the wave. Radial lines pointing outward from the source are called rays. Notice that the rays are everywhere perpendicular to the wavefronts. The rays indicate the direction of the velocity of the wave. At large distances from the source, the wavefronts curve less and less. Eventually, the wavefronts approach the shape of flat surfaces or planes and are known as plane waves. Since rays are perpendicular to wavefronts, the rays for a plane wave form a set of parallel lines and indicate the direction of propagation of the wave. For light waves, the ray concept is particularly convenient when showing the path taken by the light. We will make frequent use of light rays, which can be regarded essentially as a narrow beam of light, much like those produced by lasers.